All right, thank you. So I was all ready to cut this slide this morning when we were short on time, because I don't think I really need to convince anyone in this audience that doing high-performance computing and writing high-performance parallel programs is a really difficult job. And we should try to do whatever we can to make that job a little bit easier and improve productivity for the people who are writing these programs. So we all know that this is a difficult problem to get right and also an important problem to get right. But it's not clear exactly what we want to do about it. So a lot of this workshop is sort of about using Charm to address some of these problems. So I think Charm's a great start, and my work is sort of an extension of a lot of that. It's called Charj, and the idea is to write programs more productively using the Charm programming model by adding a layer of compiler support on top. So that allows us to do things like make the syntax of the program more meaningful, do some static analysis to provide better warnings and error messages for the programmer, and identify optimizations that can't be done at the library level that the compiler can do, and facilitate things like DSLs and little languages that can make writing programs for a specific niche or a specific kind of interaction pattern much more productive. And then we can also add language level support for a lot of the rich features that Charm offers in its runtime. So, there's been a lot of praise for Charm in this workshop so far, and I think rightly so. But let me throw a little bit of cold water on all that enthusiasm by saying that if you want to write programs for Charm, there are some pretty common problems and road bumps that programmers run into that I think could be made a lot better. So a lot of these problems come from the fact that most of your code is only ever seen by a C++ compiler, and the C++ compiler doesn't know anything about the Charm runtime system or about the Charm programming model or how different processes in your program are going to be communicating with each other. And that means there's no simple way to do a lot of things that you'd really like to be able to do, like enforcing the basic semantics of the Charm programming model. Like if you say, I have this variable, it's a read-only variable, well, the C++ compiler doesn't know or care about your read-only variable. If you write to it, it's going to get written to, and there's a bug in your program now. And this fact also makes it really hard to do any kind of compile time analysis and optimization, because most of the actual application code, as opposed to the sort of interface definition, is only ever seen by the C++ compiler. So if you want to do some kind of parallel specific optimizations, it makes it really difficult. So you can sort of try and move some of your code into the interface file and add some special sauce to CharmC to make this stuff possible, but it's a really difficult and inflexible way to try and do things. So the idea behind Charj is basically we want to add this compiler infrastructure while keeping it simple. We don't want to add a lot of new and crazy syntax. We basically just want to allow this opportunity to write more productive programs without trying to really advance the state of the art of compilers or produce some kind of crazy new revolutionary syntax that will wow people. We basically just want to have what we have with Charm, but better and more productive. And so some of the ways we want to do that are distinguishing between local and remote operations, integrating tightly with the runtime, and providing better support to the programmer. And we want to be able to do things like enforce, provide warnings and error messages to the programmer if they're misusing read-only variables, and eliminate redundant program information. So, if you have an entry method in a Charm program, the function signature for that method is probably going to appear in 3 different places, and in your header, in your implementation file, and in your interface file. And that's true for every entry method in your program. And as I said, we want to be able to distinguish between local and remote operations. That makes the programming model a lot more simple and clear, especially to newer programmers. And if we can identify optimizations at compile time and do them, instead of making the programmer do them by hand, then that's also a big win. Because I think a lot of the times when we talk about compiler optimizations in HPC, like, it's so important to have an optimized program that at some point the optimization is going to get done. It's just a question of, can your compiler do it, or are you going to have to do it yourself? So in this talk, I want to talk specifically about one kind of optimization that we actually do in Charj on communication. So data exchange in a parallel program. We want to communicate data across processor boundaries through different address spaces. So we have some data structures in the user program. We want to send those over to another address space so they can be used remotely. So there's a process of packing something into the buffer to be sent. We send it over the network. Then it's unpacked on the receiver side and used. So how do we actually accomplish this process? Well, there are a few different techniques that are used in different programming models. In MPI, usually you'll have a buffer and copy things into it, and then copy things back out if you need them, or just use stuff in place in the buffer. In Charm, the user will write a pup method, a pack-unpack method, for each type that you want to send that describes how to pack and unpack that method. Or you can explicitly declare messages and write stuff into the messages and read it back out. So this is like the explicit buffer management style of sending stuff, where you memcopy variables into a buffer and then send that buffer over the network, and then you read it back out. So this has some really serious problems. First of all, it's not type safe at all. You're just taking data, pushing it into the buffer, and then pulling it back out on the receive side. So there's no enforcement of type safety or guarantee that what you're pulling back out matched what you put in the first place. So it's sensitive to the order in which you put these variables in. If you get it backwards on the receive side, you'll just have corrupt data in your variables. And this can really be a notorious source of bugs, where you're handling these buffers and doing pointer arithmetic and all that stuff. So this is sort of the Charm equivalent, where you have some type and you write a pup method, where you basically enumerate the variables in your data type, and when the runtime system comes to marshal up your data structure and send it across the network, it calls this method. And the method is called with different pupper objects, depending on whether it's trying to figure out the size of the buffer that needs to be allocated, put data into the buffer, or read data back out. So this has some problems too. It is a very one-size-fits-all to communication. So if you want to communicate this type, you're sending it using this pup method. It's not context sensitive at all, right? So if you have two different entry methods in different parts of your program that need to use a different subset of the data in this object, if you use the same pup method in both places, you will get data that you didn't need. Redundant data is going to get sent. And to avoid that, you need to create explicit messages. It requires the user to actually go through and enumerate all the variables that they want to send. And whenever you change the data members of your type, you have to remember, oh, I need to go back to the pup method and add or remove whatever variables I've changed in my type. So if you forget when you add a new data member to your type to go and edit the pup method, you will just silently get no data communicated over the network for that new field. So to look a little more carefully about that one problem I mentioned about unneeded data, for any method, when we're talking about entry methods, some of the arguments may contain fields, and your method might not need all of the fields of all of its arguments. There might be some unneeded data in there. And for, when we're calling remotely invoked methods, we're sending this data over the wire, and it hurts performance. So we're wasting communication to send this. So here's an example. This is an actual, from an actual program in the Charm examples directory. This is functional 2D molecular dynamics, and it's written to be sort of clear and concise and not efficient, right? Since it's an example program. It's like 750 lines of code or so. And so there's this particle class that has vectors for position, force, acceleration, velocity. It's got a nice pup method that says, okay, if you're sending this thing, then pack up those members. And then we have this compute class, which is in charge of calculating interactions between these particles. So there's an interact method, which takes as its argument a vector of particles. But the interact method only actually needs the particle positions. The force, acceleration, and velocity are never actually used in that interact method, right? So the way that we're sending this vector of remote particles is pretty inefficient. Like 75% of our message is wasted. So a lot of the communication when you actually run this program is really unnecessary. Okay, so there are a lot of, it's actually worse than 75% in the real program, by the way. I've left out some extra variables just for clarity. And you could go in and change the pup function to only pack up the positions, but that would lead to bugs elsewhere in the program because this isn't the only place where we send particles. Even if it was, changing the pup method to do that would be really unintuitive and really just like begging for strange problems down the line. So one possible solution to this is to use a custom type for the argument that only includes the needed data, or to define a custom message type. So that gets rid of the big overhead problem, but it causes other problems, right? So it causes a proliferation of these special purpose types, which don't have any real semantic meaning in the program. So if you're creating a special type whose purpose is just to say, like, this type is just the data that the interact method needs, then how does that really scale up to a large application, right? You end up with all of these different special purpose messages or special purpose types, and you know, it gets to be kind of a mess. It's not like you can't handle it, but it's definitely not what you'd really like. So for an example of something that sort of implements the solution, we have LeanMD. So LeanMD is like a slightly, or a somewhat more realistic and efficient and scalable molecular dynamics app than molecular 2D. It's actually something that has, I think, shown up on some plots over the last 2 days here. I think it was part of our HPC challenge submission. It was, and it's actually been sort of optimized for clarity and length to try and, you know, make our implementation look as good as possible in terms of efficiency, I guess. And this is, you know, not even that much longer than molecular 2D. It's about 1,000 lines. And so we have a very similar situation here where we have a particle class with the same kinds of members. But here in the compute class, interact method, we have a particle data message instead of a vector of particles. And if you look inside the particle data message object, it's basically just the data that we're going to need for the interact method and nothing extra. So we've eliminated the huge waste situation from molecular 2D, but we've added a lot of extra code involved in defining the particle data message, writing data into the particle data message, and reading it back out. It expands the program, and we have this extra type who, it's not like it ruins the program to have particle data message in there instead of vector of particles, but it's not exactly great either. In Charj, we try to get around these problems. And the first thing we do is observe that, like, writing pup methods kind of stinks. And it shouldn't really be that necessary when most of the time all you're doing is looking through your data structure and enumerating the things in there that you want to pup. The compiler already knows everything that's in your data structure. It knows how to lay it out. It has to. It's the compiler. So for the sort of default case where you just want all of the data in your object to be sent, you shouldn't need to write a pup method. The compiler should be able to write one for you. You can run into a problem potentially with cyclic data structures, but we get around that problem by just tracking memory addresses when breaking cycles, when it's time to do the pup. And this has the additional benefit that when you update your type by adding or removing variables, the corresponding message packing and unpacking code changes right there along with it. And then, for special cases where you want to be able to specify your own pup, just for maximum control, you can override this automatic feature and write your own. But that still leaves us with the problem of this unneeded data with waste when we're not actually using all of the fields on the receiving side. So this is a problem that we can also address with live variable analysis. So we'd like to be able to identify which fields on the receiving side of a message are not going to be used. If we can go through and say, like, okay, on the receiving side, definitely this member variable is never going to be touched. It can't be touched in any possible thread of execution or any possible path of execution through this function, then in that case we should be able to just eliminate that variable and not send it in the first place. Well, that question is actually very easy to answer with live variable analysis. Which fields don't we need on the receiving side? It's the ones that you can't access in any path of execution. And that is all of the variables that aren't live when you enter the function's preamble. So we perform this live variable analysis, identify all of the variables that aren't live at the function's preamble, and then produce a custom pup function for that method, which only packs the data that is actually potentially used on the receiver side. So here's the Charj example for the leanMD, like this leanMD in Charj. And the particle looks the same, except that we don't have a pup function anymore because we don't need it, because Charj will generate it for us. And in the compute side, we're back to having an array of particles. I guess here it's called array instead of vector, but that's not too big of a difference. But this has the advantage that only the positions, which are the fields that are actually used in the interact function, are sent. So we're not incurring that extra overhead. And we're also not introducing these new types and overhead that leanMD needs to solve the problem. So this approach in Charj has some clear productivity benefits. The programmer doesn't need to write these pup functions in the first place, and they don't need to maintain them when they update the data structures. It has type safety, which direct buffer management doesn't have. So it's not possible to mismatch types on the send and receive side. The compiler will detect that error at compile time. And the per method pups can automatically strip out unneeded data that can't potentially be used on the receiver side. And this creates smaller messages while still preserving meaningful types at the application level and preventing the need for special purpose container messages. And I think most importantly, this sort of lets the programmer focus on the actual important higher level issues of algorithm choice and more complex optimization instead of just focusing on packing bytes into buffers and taking them back out in the right order. So it lets you sort of get to the more important issues and leave the mundane ones to the compiler, which I think is a lot of what higher productivity is about. So that is my example for the Charj optimization. And I think Charj provides a lot of opportunities for doing things like this in Charm. And I've sort of focused on one of them for the purposes of being able to give this talk in a reasonable time window, especially when cutting into the panel discussion that's supposed to be coming up. But this is, I think, one clear example of a place where having some compiler front end on Charm provides clear productivity benefits for the programmer.
Maybe not so much as a question, but I think when you think of compilers, we think of all kinds of strange optimizations that we can do and extract magically some parallelism from it and so on. And I think I've been enamored with the idea for a while, and we explored that in this thesis, that really we need lowbrow optimizations, and they can go a long way. Just that the compiler people are not interested in those. They are very high intellectuals, and only polyhedral something or the other will wake them up and get their interest. So, and the unfortunate thing about compilers is that it requires a huge infrastructure to build a compiler. So this kind of intersection of expertise is really what's needed. Finally, bit the bullet, well, not me, Aaron bit the bullet and build the compiler infrastructure for it. And we hope actually to make some headway in that direction. But it will be really good to have some compiler people that say, okay, we've done enough of the complex stuff, maybe we can assist. And I think to some extent Rose and Dan Quinlan will play that role, so on. So,
all right. Thank you.